Let's talk about the subtle art of API rate limiting. No discussion about different algorithms here. We get into the nitty-gritty of what really matters if you're trying to implement quality rate limiting for your API. We've got 8 points that we think are the best practices and things you need to think about before you pull the trigger and make sure your API is protected and offering the right customer experience. Hi. I'm Josh Twist, co-founder and CEO of Zuplo, the programmable, serverless, fully managed API gateway that runs at the edge. In a previous video, we talked about how we approach the best practices for implementing API key authentication. It's how we did it for our API gateway, but we shared that as a general guide for anybody that was thinking of implementing API key authentication. It was pretty popular, got a few thousand views, and so we thought we could keep putting videos out like this that share our experiences from all of the work we've done with our customers using Zuplo, all of our research into the best way to solve these problems, and where we landed in terms of our strong opinions about how this stuff should work. And share that with everybody in case you want to roll this stuff yourself. Of course, using Zuplo is always an option if you want to save some time. But no, seriously, we're sharing this in a way that if you're approaching rate limiting, in this case, setting API rate limiting, that is, then here are some of the best practices that we've learned. Let's start with number one, and that is a simple overview of the canonical approach to API rate limiting. So with rate limiting, what you're typically trying to do is protect your resources so that one, a rogue or malicious actor, be that deliberate or unintentional, we should talk a little bit about unintentional actors, from taking your service down. And the main reason you want to do that is, well, it might get expensive for you, but the main thing you care about is one customer or one malicious actor creating a bad experience for your other customers. And so that includes things like them consuming too much resources so that there's resource starvation and other customers are getting a bad experience and your whole service slows down or you have downtime, which is kind of the end game scenario. So that's why we actually think of this as part of our 3 pillars of an API program, of launching an API. The pillars are authentication. You need to secure your API. We talk about that in the API key best practices. You need protection. So that's where rate limiting comes in to ensure that your API is protected. And you need some way of helping developers on board. So we talk about that being documentation. Those are the 3 core pillars upon which you start to build your API program. There's lots more to think about. With protection, you need that because, again, there are malicious actors out in the world who will hit your service. But that isn't the main reason. That isn't the main thing that's going to happen. What's going to happen is one of your own developers is programming against your API and they have a bug in their React code that causes an infinite loop because of the recreation of state or the way they're using useEffect. And that is going to hit your service so hard, it's going to take you down and your other customers are going to have a bad experience. Or one of your partners is going to onboard. This happens all the time. I talk to customers regularly and more than half had this happen in the last few weeks. One of their partners was onboarding to the API, had a little bug in their code with a for loop, and boom, your service was hit very hard and taken down. So we always want to have some form of rate limiting protection in place. Now, rate limiting typically takes the form of, if you're going to implement this yourself, of some counter. So you're setting a rule that says, I will only accept 100 requests per minute or 1,000 requests per second, some sort of rule like that. And you're going to count the requests coming in, and you are going to work out, when that's exceeded, you're going to stop serving requests. The typical way to do this, or the canonical way actually, in HTTP APIs is to return a response with the status code 429, which if you look up on MDN says too many requests. And that's really all that is involved. If you want to implement rate limiting today, probably the quickest way on a simple project is to find an open source library. There's a Flask limiter for Python. There's Express rate limit for Node users that are using the Express runtime. There's lots of choices out there for simple scenarios. There's not so many choices for complex scenarios, and we'll get into some of those later. But that's how you would effectively implement a canonical rate limit. Do some counting. Remember the time period at which it started. Once you hit that count threshold, start responding 429 until that time period is expired. Now, if you do any research on API rate limiting, what you'll typically find in most articles is debates about whether you should use the token bucket algorithm or the sliding window algorithm. And they're good debates, they're good topics, but frankly, there are more important things to sort of concern yourself about your rate limiting design and the experience you're creating for your customers. So we're going to focus on those in this video, and I'm not really going to get into algorithms. There's tons of content from everybody out there about the different algorithms. Happy to take questions in the comments if you want to know how we do it, but that's not going to be the focus of this. So instead, we're going to focus on rate limiting. So the final point I want to make on that canonical implementation, if you look at the MDN documentation, you will see under the response 429 too many requests, there's already also a suggestion that you should include a retry after. So what that tells a client is if they're hitting your API and you respond with a 429 too many requests, it tells the client that they can retry after this many seconds. So it actually tells the client, hey, back off, but you can come back at a certain time. So that is, to a T, very straightforward, how to canonically implement rate limiting. Let's get on to point number 2, which is whether you want to be public or private about your API thresholds. So what does that mean? Well, if you have a public API that is free to use, you actually might not want to share what your API rate limit thresholds are, because it allows for a malicious actor, in this case, a deliberately malicious actor, to kind of optimize how much they're going to get out of your service very easily. You know, if you send them back, if they hit your rate limit and you send them back a response that says retry after 30 seconds, they can very quickly calculate what your rate limit and time period thresholds are, and then they can set up their system to just fly under the radar, not get any 429s, and perhaps go unnoted by your system, but are maximally extracting everything they can out of it. You might want to avoid that. If that's the case, for certain APIs or certain consumers of your API, you might want to choose to be more private about your thresholds. If that's the case, don't send back the retry after header. It's not mandatory. You can just send back 429 too many requests and say back off. You could be even more secretive and just send back a 400 bad request and not give any information. It's not very helpful to most of your customers, so I personally wouldn't recommend that. But for that reason, in Zuplo, our rate limiting policy is configurable. You can turn it into a sort of private or public mode, in which case we won't send back details of retry after if you're in the private mode. Now, if you have business-to-business customers using your API, perhaps you have a contractual agreement with them, which includes the term your rate limit thresholds, then absolutely you should share your rate limits with those people. And you should probably include the retry after header because you have a known relationship. The actor is a known quantity to your system because they'll be somehow authenticated. And so it just makes sense that you're going to give them the best possible experience and let them know when they're hitting your rate limits and when they can come back and try again a little bit harder. In that case, you kind of have a trusted relationship with the person. And so you should feel much more comfortable sharing information about your sort of peak, your rate limit thresholds and timings that you want to do. So for the next section, for the third point, want to think about how you would apply rate limits. And we actually just started to get into this a little bit with the notion of a known actor and an unknown actor. So when we do rate limiting, we typically think of buckets. You'll come across this if you look into the algorithms section of how to do rate limiting. And the bucket is, how do I group together these requests? Do I just count all requests coming into my service and say there's only going to be 1,000 per second? Well, in a way, what we said was when you implement rate limiting, what you're trying to do is stop one actor, be the malicious or accidental, known or unknown, from creating a bad experience for other actors. Now, if you have a global rate limit, you've just created a very easy way for someone to create a bad experience for another actor. Because all they do is hit your service with lots of requests, and suddenly other users are going to get a 429 too many requests. So global rate limiting, it might be useful as a backstop to ensure that you don't end up spending all of your cloud resources and a lot of money on a DOS attack. It might be useful in that case, but generally it's going to create a pretty terrible user experience. So that is what I think of the the lowest or the bronze medal of rate limiting. In fact, global doesn't even get a medal. It's not even going to be on the podium. It's generally just a backstop for distributed denial of service attacks and making sure your whole service doesn't go down. It's going to give a pretty bad experience to your other customers. So then maybe we do IP-based rate limiting. So, IP addresses tell us where the caller is coming from on the internet. It's an internet protocol address. And so now if I'm getting attacked by a user behind one IP address, I could just count for that IP address and block that IP and still give access to people using a different IP address. So that's pretty good. I'm going to give that a bronze medal. That's definitely a step up from global rate limiting. But there are tons of problems with this. It's pretty easy to spoof IP addresses. So someone could pretend to be an IP address of another customer. What's up more so is, people can share IP addresses through no fault of their own. So, if I'm in a WeWork office using my device and some other person is at a WeWork office using a different device, don't even work for the same company, they might both be hitting your API from their mobile device over the Wi-Fi or their laptop. They're probably going to appear through the NAT of the WeWork office and be appearing from the same IP address. So again, if that person is hitting the service too hard, it may impact my experience. So not perfect. Same with data centers actually. So if your workload is running on Google Cloud or running on Azure or AWS, it is possible that you're sharing an outbound IP address with other services running in that cloud. And so again, you get this problem where one customer can create a bad experience for another customer, which is really at the heart of what rate limiting is trying to prevent. So let's call IP address rate limiting the bronze medalist of this scenario. So how do we go better? Well, what if we could do user-based rate limiting? Now, if you have a public anonymous API, then you're probably stuck at IP-based rate limiting being your best hope. There might be some other techniques like user agent fingerprinting for browsers and so on, but probably too risky. You're going to just create accidental problems with that. So IP address is probably decent. But the minute you have an authenticated API, then everything changes. You now know because of a JOT token or an API key who a specific user is, even if they're using different IP addresses. So actually that's another problem with an IP address is one user might be able to use a lot of IP addresses and still consume a lot of resources. Just by fanning out the IP addresses, they can consume a lot of resources and give a bad experience to the customers. So again, IP is not perfect. However, if they have a token that identifies them as a user, you can now be sure, no matter how distributed that overuse is by that user, it's coming from that user. So being able to count by users is the silver medalist here. I think that's probably the almost the best option for how to implement your rate limiting. So how do I get a gold medal? Well, the reality is rate limiting, you may need to apply this differently based on who that customer is. So if you're a B2B SaaS and you have an API, you probably have some free tier customers. You probably don't want to give your free tier customers the same rate limits as your premium enterprise customers. Those folks are paying you lots of money, and so therefore they're allowed to take your service much harder. This becomes a much trickier thing to implement. You now need kind of smart dynamic rate limiting, we call it at Zoopla, where you can vary how the rate limits are applied to each request based on fairly arbitrary properties like, hey, is this a free customer, a premium customer, which route are they using, etc. And so that's something you should really think about when you're designing or implementing your own rate limiting solution. Now in Zoopla, we built this. We built a dynamic rate limiter, and in just a couple of lines of JavaScript, you can dynamically assert how an individual call should be rate limited based on metadata for the customer, based on a database lookup and caching. It's pretty powerful. So, Zoopla is an option there. But if you're designing this yourself, that's something you really want to think about, because you almost certainly don't want to give low-end customers or free users the same API rate limits you're going to afford your largest and most important customers. So those are the different ways to think about the bucketization or the tokenization of rate limiting, and something to think about. The next thing, how to think about rate limiting with distributed systems. So if you have a single server that is accepting your API requests, then implementing rate limiting is extraordinarily easy. Go and look up which algorithm you want to use, token bucket, sliding window, etc., etc. And simply, you could just do this in memory. You just write a little bit of code, a little bit of middleware for your API that is going to count in memory for each token bucket. You might have to write some custom logic here if you're going to do custom bucketed rate limiting, as we just described. And it's very easy because there's just one machine. So all incoming requests all around the world are going to get routed to that one machine. Now, we know that's a bad design because it doesn't scale. It doesn't offer high availability. If that one machine goes down, all of your customers are without service. And we're not even getting close to, being globally distributed, which is where most of the world is trending towards now. So let's imagine we upgrade our system a little bit and we now have 2 machines or 3 machines. They're all located in the same data center. But now, if we count in memory, then we have to hope that all requests come into the same server, perhaps, to keep the count of each individual token bucket in the right place. Otherwise, we're now forced to do some synchronization across those 3 servers that we have. Right? Somehow the counts are going to have to be synchronized across them. And that is possible. You can use a service like Redis in the background behind those 3 servers, which can be very high performance, and use it to increment the counts and check the counts on every request. So imagine a request comes into a server, you identify the user, you're building custom like gold, medal level rate limiting, and you are now, what you're going to do is you're going to do a check to say, hey, how many requests have I had from this particular token situation in the last 1 minute, whatever the timer is, and can I allow this request to go forward? So you'll start to see what we're building in now is a little bit more latency. If we're doing that in memory, we're talking microseconds, it's fine. Now we got to do a hop to a Redis instance across those 3 things. So we're probably adding multiple milliseconds of latency to the check and some complexity to our infrastructure, because that infrastructure now has a Redis that's got to be, also needs to be redundant and managed and deployed, etc. But, at least you've solved the issue. What if we start to get really distributed? So now I have multiple servers in the Asia region, in the Americas region, and in the European region. Well, now we have a problem with where do we put the rate limiter? If our customer base is equally distributed, the rate limit synchronization point would be that Redis server that we just talked about. Do we put it in Asia? Because now those folks in Asia will have reduced latency on the rate limit check before they get into the actual call of the back end. But customers in the Americas will have significantly increased latency. So perhaps you're going to have a replicated Redis across all those 3 servers with some replication taking place. So you can see distributed rate limiting becomes a very non-trivial problem. There are some open source projects that try to tackle this, like Gubernator. I'll include links at the bottom. I'd love your thoughts and, by the way, and your comments and pushback on some of the things I'm describing here. I look forward to you getting feedback on that. But that's where things get somewhat more complicated. And then the hardest scenario, which is the one that Zuplo faces, and we had to factor into our rate limiting capability, is if you're edge distributed. So our gateway runs at the edge in almost 300 data centers around the world, and yet we guarantee you that when you are using our rate limiter that we are synchronizing those counts. Now, we put a lot of work into making this high performance. So we have a Redis-like service that's doing the counting. We have synchronization taking place between nodes that are distributed around the world. And then we do a lot of smarts with local edge caching, some in-memory caching to improve the performance of the rate limit, so you're not paying a long wait time for us to do that rate limit check. And then we also have some really advanced stuff that I'll get onto as we look at the latency accuracy trade-off as well that we can bring. But once you get to edge-based API hosting, rate limiting becomes much more interesting, much harder if you want to keep the latency of that API check down. Now, again, easy option there is use Zuplo. We've taken care of all that for you. It's very turnkey. It's very easy, including the custom gold medal rate limiting that works as well with that system. But if you're going to implement this stuff yourself, that's something you want to go in mindful of what you're going to have to deal with and think about to have a high performance rate limit capability. So let's talk about point 5, which is the request latency. I actually kind of got into this just now when I talked about distributed systems, but I just want to really make it super clear what's happening. So When you implement rate limiting, you have to protect the backend API from being hit by consumers that have exhausted their rate limit allowance. And so to do that, what we do is we front load the request limit check in front of the backend call. And that request limit check is going to take some time. If you're doing an in-memory counter on a single server, it's going to take microseconds. If you're doing distributed, it's going to take many milliseconds. If you do globally distributed badly, it's going to take hundreds, maybe thousands of milliseconds, and add that to your overall API latency, which you don't want to do. It's a real problem. And so this is something you have to think about. With Zuplo, we call this strict mode. We are being very strict about ensuring that somebody hasn't consumed their rate limit quota before they're allowed to call the backend. So that's strict mode. And that brings us to point 6, which is the latency accuracy trade-off. Everything in engineering and in product is essentially can be boiled down to some kind of trade-off you're making. And the downside to strict mode is that every customer pays that price. Every customer on every request where they have not yet exhausted their rate limit quota is going to pay that extra latency. Maybe you don't want to do that. So the other world is where you run the rate limit check asynchronously, which is an option on the Zuplo rate limiter. You just set up the mode correctly. And what happens in that world, this diagram will show you, is instead of front loading the full rate limit check, all we do is check a number of local caches in this case to say, has this user recently been blocked? And if so, we'll keep blocking them. We'll just send a 429 response immediately, and we won't hit the back end. In the other case where the cache says, no, this user hasn't recently been blocked, what we can do is we can run the rate limit check in parallel with the backend call. So now you're paying much less of a penalty on most requests for the rate limiting check. The downside to that is if it then comes back that user has been rate limited, they'll still get a 429, but we will have also invoked your backend. But when we find out that user's rate limited, we'll set a local flag in memory and in cache that says, hey, the next time this person makes a request for the next 20 seconds or whatever the time period is you set, we will block them using the cache so they're not going to keep eating the resources. So the trade-off is a little bit of accuracy. It means you might get a small, typical low single-digit % increase over the actual allowed quota where the person is invoking the backend. They're still getting no benefit from it because they're still going to get a 429. But in many cases, that's a better trade-off because honestly, most of the time, you are not rate limiting people. You are not giving them a 429 too many request response, but everybody's paying the full price of the latency for that check. So thinking about that latency accuracy trade-off is an interesting thing to think about when you're doing rate limiting. Do you really want to add, tens of milliseconds potentially to every call in order to check the rate limit, when you could probably do it much more quickly if you do it async and take a risk of a few more calls that you weren't expecting? That user's still going to get blocked pretty quickly if you implement your caching strategy, which is non-trivial, if you implement your caching strategy correctly. So I think that's an important thing to think about. Okay, so I think we're on point 7 now, and that's about observability, which is a really important topic because we've talked about the implementation of rate limiting. You're probably feeling excited. You're ready to dust off your coding fingers and start writing your own rate limit policy and deploying your own distributed Redis and synchronizing those things and building in a cache layer so that you can do async really well. It sounds like fun. There's more things to think about beyond the basic functional requirements of the rate limiter, and that is observability. So the bare minimum you can ship your rate limiting function and feel sort of comfortable you know what's going on is that you must have some counter. You must have some performance metrics that are telling you how often am I sending rate limit responses. Otherwise, you have no idea which customers are hitting it. You have no idea if this is being triggered. In some cases, you might need to set up alerts based on that. If you're pumping data to Datadog Loki from Grafana or New Relic or any of those folks. You want to be able to set up those alerts or your own custom reporting solution. And those notifications, those counters need to be able to be broken down by customer. Because you need to know which of your customers, if you're doing user authentication, are actually hitting the rate limits that you have defined. This is the bare minimum because you're going to have to reach out to them, perhaps upsell them. They're going to maybe not have good logging themselves and not know what's going wrong. You need to be able to identify very quickly, hey, our rate limit functionality is being triggered heavily by this particular customer or this particular user, and decide what you want to do with it. Do not ship without this. It is a bit of a nightmare Sherlock Holmes game when you start to get calls from people saying, hey, I'm getting rate limited here, what's going on? So that's the bare minimum. But actually, before you implement rate limiting, and I think this is kind of point 8, how do I know what rate limits to set? It's a really tricky question. Is it 1,000 per second? Is it 100 per second? Is it 10 per second? And I think there's a number of factors that feed into this decision. And what I typically recommend people do is they have analytics set up on their API so they can actually see what the RPS is, what the request per second or request per minute is for some of their different customer profiles. And so you want that broken down by user, and you want to be in observe mode probably for a little while and set slightly higher rate limits than you imagine you need until you've done some observation. But once you start to see what those trends look like, what are the peak times? When do the peak hours come in? What does a busy customer look like? You'll probably have some sense of where you can sensibly set a rate limit with some threshold just above what that peak looks like, and have confidence that you're not going to give a lot of customers a bad experience. The other approach to setting rate limits is often based on business and pricing. So, if you look at Twitter, for example, they will sell you different packages or bundles of, not that they're the sweetheart of the API economy anymore with the very high prices they've put on their enterprise offering, but it's an example nonetheless, where you can, they've set based on the business model that we will throttle you to a certain amount of API traffic based on the tier that you're paying for. So that can be another actually way of even monetizing your API. If you have an API that's popular, then you can charge customers more to allow them to have higher rate limits, and that will also inform your rate limit strategy. But again, to see that in action, you need as a minimum on your observability, you need to know how many times a 429 is being sent. Can I break them down by user and by token, by token? And can I also see the RPS with the same breakdown so I can again understand where people are peaking out? Anyway, I hope you found this useful. We have a blog post with the same written content that I'll include in the notes below. I'm really interested to know what you think about this content. Do you find it useful? Any comments, anything you disagree with in terms of what I've said? I look forward to some debate down in the comments. And thank you for listening. Again, I'll have a link to some of the open source solutions that we recommend. But if you do want to have the easy path for all this, especially for distributed edge-based rate limiting that's super high performance, then you might want to give Zuplo a try. Try it out at zuplo.com. Thanks for watching, and stay tuned for more videos like this. Thanks.